Okay, so what we're going to continue talking about is something called work. Okay, so work is one of those words in physics that has many, many different meanings. If you meant to say that you're going to work, that means you're going to go do something and maybe, hopefully, get paid for it. Maybe you did some work for your parents or something like that, where you are out there just doing something. Well, in physics, we have a very specific definition for work, and it happens to be an equation. The equation for work is a force multiplied by a distance. And the thing about the force and the distance is that they have to be going in the same direction. If they're not going in the same direction, then we have some work ahead of us. So let's just take a look before we even do any kind of calculations as far as the units for this. So force is measured in newtons, right? We know that force is measured in newtons, named after Isaac Newton. And we multiply that by a meter, okay? Well, a newton is a composite unit. A newton is a kilogram meter per second squared. A kilogram meter per second squared. That's mass times acceleration. I multiply that by a meter, and that gets us a kilogram meter squared per second squared. Okay, but this might seem very familiar to you because a kilogram meter squared per second squared is exactly a joule. Okay, so we have something here, work, force times distance, that gives us the same unit of what we've been talking about. It gives us the same unit as energy. So let's think about what that means. Well, let's look at a problem. So our first problem is a box. And this box is on a frictionless table, frictionless surface, and it is being pulled forward with a force of, let's just say, 15 newtons. Okay. Now that box gets pulled for a distance of 12 meters. Okay, so we have a force and we have a distance, and this distance is, if we really talk about it in terms of the vector form, it's displacement, right? So the displacement from this box from here to here is equal to 12 meters, and that displacement is in this exact same direction as the force. So that means that the work done is force times distance or displacement, which gives us 15 newtons times 12 meters. 12 meters, there we go. And therefore the work done here is 180 joules. Okay, so where did this work go? You transferred the box from here to here. Well, the where it went is in the fact that from getting the box here from position 1 to position 2, you had to get it moving. Okay, so this box here, or this work here, is expended in the kinetic energy of the box as going from here to here. Okay, so this work is tied to the energy that was used or given to the box to get the box from here to here. Now, I told you that force and distance have to be going in the same direction. So what if they're not? Well, if we have the exact same box and it is now being pulled up with an angle of, say, 20 degrees, and it's still the 15 newtons of force, and it's still the 12 meters, then we have to ask ourselves, is the entire 15 newtons of this force actually going to get this box from position 1 to position 2? Well, you can see how not all of it is. The only part of this force that is actually going to move the box is this part down here. Okay, and you can continue out this triangle if you want, but we're really only interested in this one part down here. This is the x component of that force. Now, to solve for this x component, we could do the actual force, 15 newtons, and multiply it by cosine of 20 degrees. So when we come over here to solve for the work in this case, we would have to do force in the x direction times distance. And we can say that that's, okay, f cosine of the angle, okay, that quantity, which is the force in the x direction, times distance. And most of the time it's going to be cosine in these situations. You won't see very many where this won't be cosine, and it might be sine. So we can actually say, okay, in general, work is equal to FD cosine theta. And in this case up here, cosine of theta, that's just equal to 1 because theta is 0, the angle between the displacement and the force vector. There's no angle here. It's 0. And if you stick that in your calculator, cosine of 0 goes away. But in here, we actually do have 1. So if you put that in, we would have 15 newtons times the 12 meters times cosine of 20 degrees, and you stick all that in your calculator, and you get the fact that it comes out to 169 joules. So did you do as much work as you did up here? No. It might have seemed like you did more because you're pulling on it, and not all that force went to moving it, but you actually did not do as much work. Now think about this. What if you had pulled straight up? What if you pulled straight up, and maybe this box is heavier than 15 newtons? Is the box going to go anywhere? Well, the answer would be no. If it's heavier than 15 newtons, then this is just not going to cut it. So do you do any work in that case? No, because this box doesn't move at all. Your distance in that case would be 0. So work is dependent on the amount of force that actually gets something to move. Okay. Now, what could be different in these situations is how fast you did either one of them. And how we would calculate that is something known as the power. Okay, power is the rate at which work is done. Now, power is the rate work is done. So if it's a rate, then we can say power is equal to the amount of work done divided by the time it took to do that. So these have different works, but if you did them in the exact same amount of time, then it took more power on one than what it did the other. So let's just take a look at this bottom one where we pulled up at an angle. So the work we did was 169 joules, and we're going to divide that by, let's just say it took 30 seconds. It took 30 seconds to go 12 meters, okay, which is, I don't know, you might be able to do that. And if you just stick that into your calculator, 169 divided by 30, then you would get 5.63. Now what's the unit here? Well, we have a joule per second. A joule per second is something that we call as a watt, a 5.63 watts. Okay, and that is spelled W-A-T-T, or with an S on it if you have multiple. So watts, that is the unit for power. It's also known as a joule per second. And you can go all the way back up saying a joule is a kilogram meter per second squared, and you figure out what a watt is if you really want to. Okay, but that is power. So the power is the rate at which work is done. So work divided by the time. Okay, and you might see or might be familiar with the unit of watts if you've ever looked at the top of a light bulb. Let's see if I can draw a light bulb here. That's not bad. There you go. Okay, so, and there's the filament. And we know that the filament heats up and it glows, so you have light coming off. And if you take a look at maybe the top of it, you'll say that you're using a 60-watt light bulb. So what does that mean? That means for every 1 second, you are using 60 joules of energy. Now, how is that energy coming out? Well, it's coming out mostly in light. It's also coming out in heat. If you touch one of these after being on for a while, it's coming off as heat. So here's a question. How much energy is used in 4 hours? Okay, how much energy is used in 4 hours? Well, we know that the power is 60 watts, and for every 1 second, we use 60 joules of energy. So how many seconds are in 4 hours? Well, you can multiply that by 60 minutes in an hour, multiply that again by 60 seconds in a minute, and you end up with something that says, okay, there's 1,404, or 14,400 seconds in 4 hours. Okay, so if power is equal to work or energy, right, it's kind of the same thing here, divided by the time, then the amount of energy or the amount of work is, and let me extend the page here, would be equal to the power times the time, or 60 watts times 14,400 seconds. So in a 4-hour period, so maybe you go home, you flip on your lamp, and it's a 60-watt light, you have used 8.64 times 10 to the 5th joules. And that's quite a bit of energy that you have just used in your light bulb. So let's recap in the terms of these quantities. We have work, which is the doing of something, having a force multiplied by a distance. And then we have power, which describes how quickly you can do work. And it turns out that all this is related to energy. How quickly can you do energy? What kind of energy gets transformed when you do work? Okay, we will talk more about this tomorrow.